pleased to introduce the speaker for this session, Alex Graham. Alex started his career in engineering simulation in a Formula One team using computational fluid dynamics intensively for aerodynamic development of a race car and pushing the limits of HPC technology to go ever faster. Since joining Siemens, he has more than 10 years of experience of working with customers on a wide range of industrial applications, from flying boats to pharmaceuticals and much in between. Today, he helps to tell the world about what Siemens and the Simcenter portfolio of simulation and testing solutions is doing with cloud computing and software as a service. It will now be our pleasure to hear from Alex Graham.
Hello and welcome. I'd like to start off by taking you back just over 300 years to when Thomas Savery invented the first machine that could reliably, perhaps not very efficiently, convert the energy that was stored in fossil fuels into useful kinetic energy. Now, this device heralded the start of the first industrial revolution, and actually in the beginning it could only convert about 1% of the available energy into useful motive power. Since then we've come a very long way. All of the refinements and developments that followed on from this initial invention have given rise to one of the biggest transformations in the quality of life that our species has ever seen. It also led to a rapid rise in population and a huge demand for cheap energy. Today the population of the world is around 8 billion, and the UN predicts that by 2056 that number will be 10 billion. Cheap energy is critical to improving and developing quality of life the world over. So we all know that there's a huge challenge ahead of us as a species. We need new technologies, breakthroughs, a lot of innovation. But also the way we value and use energy needs to change. And a big part of that is making sure that the energy we do use is used purposely as efficiently as possible. And that's what I would like to talk to you about today. So my name is Alex Graham from Siemens Digital Industry Software. And over the past 10 years or so, I've been working with lots of our simulation products and our customers across a whole range of industries and applications. And today, I'm excited to share with you some examples of what Siemens and our customers have been doing to improve the way that we work and improve the way that we consume energy today. So how can simulation help? What do I mean by simulation for a more sustainable world? Engineering simulation is a branch of computer-aided engineering, and it's all about predicting how a product or a device performs under a certain set of conditions. It can be about reducing the risk involved with trying out a new concept, since you don't need to build a prototype or have a test bench model to try something out. It can also be used to optimize an existing design, something that you've already arrived at. And with simulation, you can test many more designs to tweak all sorts of different parameters, much more than you'd be able to do if you needed to build a new part every time. And of course, you gain a whole lot of insight into the process. You can see exactly how your product is interacting with its surrounding environment. So today I'm going to show you one example of how simulation can be used to enable new technology development. And I'm also going to look at an example of simulation refining an existing product. So let's get started with the first one. Now, it's especially apparent right now how important natural gas powered turbines are in filling the gaps in our energy supply. So the turbines of today are really very impressively efficient thanks to the DLE, or dry low emissions combustion technology, in which air and the fuel are pre-mixed and the combustor is operated close to the lean limit. However, increasingly we're asking our turbines to run partial loads or to ramp up and down frequently, and this can give rise to thermoacoustic oscillations or instabilities in the flow. And this is something that can be very damaging to the turbine. It can cause significant damage if they're not controlled, and it can cause the turbine to be shut down. Another cause of instabilities can be using different fuel mixes, and this is becoming increasingly important as other fuels such as hydrogen and ammonia, so synthetic non-fossil fuels, are becoming increasingly important. And so it's critical that we know how gas turbines are going to perform with those different fuels. And changing the fuel changes the flame shape, it changes all of the dynamics inside the combustor. And Siemens Energy have been using CFD to model these instabilities using very high fidelity techniques. They give them that sort of virtual test bed that they need to make these developments. And they summed up nicely what simulation lets them do in a nutshell. So it gives them sufficient understanding of their product that they can actually get to answering the question, how can I change the flow field to improve the dynamic performance of my gas turbine with fewer emissions and more stability? So in other words, how can I change the design of my product to make it do what I want to do? And to be able to answer that question for a product as complex as a gas turbine is really very impressive indeed. And they went on to comment that actually the thing that's been holding them back is computational power. And it's only over the last 2 to 5 years that this has really been possible. And luckily, there are some big leaps being made in solver and HPC technology. And of course, we'll get onto that later. So the next example I'd like to share with you is all about getting that extra few percent of performance out of an existing design using the latest simulation and generative design techniques. So EDAG is one of our customers in the automotive industry, and they were working on an electric vehicle battery pack, the cooling circuit. They were working with us to optimize this particular component, which you see circled on the slide here. So this is a flow splitter and a return line packed very closely together. So the packaging constraints really limit what this device could possibly look like. But still, using a simulation-driven design approach, we were able to make these gains that you see on the slide. So almost 50% change in pressure drop and a 7% improvement in mass flow rate through the cooling channels. And that, of course, equates to an improvement in cooling efficiency and an energy saving in terms of the effort needed to push the fluid through the system. So meanwhile, the design time actually falls because you don't need to design and test and refine and go through that cycle. We actually go directly to a design which satisfies the needs of the flow itself. So this is shown nicely in this video. As we zoom in on the component, what we see is this is a design that was created by a human, which is pretty good. And then we see a bounding box placed on that geometry. So that's the packaging constraint. Then the algorithm simply removes any material that's not helping it to achieve its target. And so we naturally end up with quite a sort of organic shape. And as you can see, it's not far off what the original designer came up with. It's almost as if the pipes have been joined in a different order. But this is the way that the flow prefers to go, and it results in a more efficient design. So it's a great example of how simulation is now enabling us to push the design of even a simple component like that and find more of these small efficiency gains, which of course all add up. So the really interesting and exciting use cases for simulation all have one thing in common. They're all possible due to the relatively huge computational resources that we now have access to. And yes, that compute is expensive, both in monetary terms as well as the environmental impact. So we need to figure out ways to reduce that environmental impact, even if the compute itself is being used to maybe solve some of the big challenges facing us, make some of those breakthroughs, and improve energy efficiency of the products. So one thing to look at is what's powering the data center. And I'm showing you 3 examples here of customers of ours who've moved large data centers to places like the Nordics, where they can be close to green sources of energy and reduce their carbon footprint that way. And this is a smart way of using what we have on a global scale more efficiently. So other things that we can do to reduce the environmental impact of simulation are to improve solver technology and to improve HPC technology. And we'll take a look at both of those things as well. So of all the simulation disciplines, computational fluid dynamics is definitely one of the most intensive. CFD involves modeling and solving the laws of physics that govern fluid flow. And by a fluid, we might be talking about a gas or a liquid or both together. On top of that, we may also be including stress, heat transfer, particle flows, electromagnetics, and much, much more, including the way that all of those different materials and phenomena and media are interacting with each other. Under the hood, it's a lot of number crunching. The volume containing the fluid has to be split into millions or billions of cells, and with each cell being directly connected to a number of neighbors as well as indirectly connected to the whole of the rest of the model, the solver has to work very gradually towards a solution where all of the cells and all of the flow is in equilibrium. It's even more complex in a simulation like this, where we're looking for the transient behavior of the flow. So that also has to be done at a number of points in time to build up a picture of how things change. So the mesh is actually what you see in the example on the screen right now. So if you imagine that whole volume is filled with a sort of honeycomb type structure, it can be honeycomb, it can be a sort of grid. But the mesh is not usually shown in a video like this, otherwise you wouldn't be able to see what the flow was doing. So what you're actually seeing there is the imprint of the mesh on the surface of the landscape where the wind turbine sits. But what you can see is that the resolution of the mesh is definitely changing there. So it's quite coarse on the outside, around far away from the turbine, but then it's very fine where the turbine is. And that's just like pixels on a TV. So far away from the turbine, we're looking at like a dot matrix display, and close to the turbine, we're looking at sort of 4K resolution, because we want to be able to resolve what the flow is doing. So we need to have lots and lots of data points to do that. So in this case, you can see that the mesh has been refined close to the turbine in a fairly manual way. But this is actually something that we can change to make a big improvement in efficiency. So in this example, you're seeing a planing hull moving through waves. And in this model, the water flow and the air are both included in the simulation. And of course, there's a sharp interface between those two, which is the water surface. So the difficulty is that because the boat's moving through the waves, it's dipping up and down and the water's splashing and breaking up into droplets. We don't really know where it's going to be. And so to refine the mesh enough to be able to capture the water surface in all cases would inevitably be quite inefficient. So what we see happening here is an adaptive algorithm which is automatically refining the mesh where the water surface is. So it's adding and removing cells all the time. And this means that you can then run the model much, much faster, or you can run it in more detail at the same time. In this particular case, this is an industry standard benchmark case, and this actually gave a speed up of about nearly 3 times just by implementing a different meshing algorithm. So adaptive mesh refinement is just one example of simulation technology which can really improve efficiency, let you do more and consume less power in the process. So car aerodynamics is a field of ever-growing relevance as electrification continues to transform the industry. And aerodynamics is especially relevant for electric vehicles for 2 reasons. So the first is the obvious one. If you can improve the aerodynamic drag, then you can get more range from your battery. The second is that without the masking soundtrack of the engine, the occupants of the car are now going to start hearing much more noise from things like the side mirrors, the sunroofs, the HVAC systems, and the external aerodynamics. And that's why simulations like the one you see here are becoming increasingly common. So what we're looking at here is a simulation of the unsteady airflow around a car using the large eddy simulation turbulence modeling technique. And by the unsteady flow, we're talking about resolving all of those little fluctuations and eddies that are produced by the flow as it passes over things like the windscreen wipers and the side mirrors. And if you cast your mind back to the computational mesh that we were talking about just a few minutes ago, you can probably imagine that the simulation like this is incredibly expensive to do. What's more is the solver would also have to be using very small time steps to follow that evolution. But the interesting part is that we've recently been able to achieve phenomenal speedups on this kind of simulation by running the solver on GPU hardware. So take a look at these numbers. This chart showing the speed up achieved on a benchmark case following the industry best practices from the third automotive CFD prediction workshop. So the mesh contained 130 million cells and was run for 16,000 time steps, and that equates to about 4 seconds of real time. So running that simulation on 10 HPC nodes, so that's 400 CPUs, resulted in a wall clock time of about 60 hours. Moving it to one node containing 8 NVIDIA GPUs meant that it took about 20 hours, and then using 2 nodes brought that down even further to 12 hours. And that's a phenomenal saving for a very, very high fidelity simulation like that. GPUs can also make a big difference to aeroacoustic simulations, so these very computationally intense calculations are really critical to understanding how noise can be produced from components like wing mirrors and sunroofs, and how that can contribute to the sound which is actually heard inside the cabin by the occupants. So the speed up here is similarly impressive, and this is using an acoustic wave model that's also recently been ported to run on GPUs in the latest release of Simcenter Star CCM+. And the amount of energy saved follows pretty much exactly the same pattern. So the comparison here shows both of the examples that we were just looking at. By making use of GPU hardware, the speed up achieved makes the overall simulation 70 to 80% more efficient, which is a tremendous saving. Now the disclaimer here is that GPUs don't really work for every single type of CFD problem. So depending on the case and crucially what kind of physics you're modeling, they may or may not be suitable. So CPUs may still be the way to go. But we're actually seeing really great steps being taken there too, which would benefit CFD workloads. So for example, the recent AMD Milan X series, which can produce beyond linear scaling due to the ultra efficient cache, which is something that we'd never really would have thought possible. And there's more too in the pipeline. We've been working closely with NVIDIA on the Grace ARM CPUs, and I'm really excited to see the results of that work. We're also going to see much more focus on attributing carbon footprint to simulation activities, something which has generally escaped much scrutiny in the past and we're seeing increasing customer demand for. So in today's world, the hardware that you're using is more important than ever, and this is something that we seek to address by constantly working with hardware and cloud providers to benchmark our solutions and understand how to leverage these new developments. We also now offer our customers instant access to cloud compute as a turnkey service called Simcenter Cloud HPC. One of the aims there being to bring them the best hardware, and it's out there pre-configured and optimized for our tools so that they can get the best simulation running in as little as 2 clicks. All of these developments together are massive, and they really transform the value proposition of big compute today. So in contrast to the rather dreary image of the Industrial Revolution that I started this talk with, I'd like to finish with this more cheery view of a sustainable world that we can build today with simulation and test. There's a lot of work to be done, and it's one thing is for sure, that simulation, test and big compute are going to be a huge part of it. Thank you for your attention.